back. In the last class, last few lectures actually, we have been talking about calculating partial molar properties through analytical and graphical means. In today's lecture, I will start with the ideal gas mixtures and basically to find out the changes in the properties of ideal gas and using the definitions of the partial molar properties which we have learned. Let us go with so let us start with the basic definition of ideal gas. So, it is a PV nRT, right. That is a equation of state where we say that the ideal gas mixture does not have any interactions. The only thing which has in its internal energy is the kinetic energy. So, this is NT, total number of moles, which I can also write like this NiRT. So, let us extend our learning of partial molar properties to ideal gas mixtures. Here, if I want to obtain the partial molar volume of a ideal gas component here, then I am going to take the partial derivative of V with respect to Ni Tp, right. Okay, and then if I use this equation of state here, replace this equation of state V from here, the equation of state, then I should be able to write this as right, and this is again summation Ni. Okay. So, RT and V is not dependent on Ni, and here from here that partial derivative of this term with respect to Ni is nothing but 1. So, what you obtain is RT by P here. This is P. Okay. So, this is for the ideal gas. The partial molar volume is I of ideal gas is nothing but RT. Now, let us look at for the case of the pure component ideal gas. So, at a given temperature and pressure, molar property of pure component, okay, I in the ideal gas, right, would be written as something like this, right. It is a V I. This is one nomenclature. I can write, since it is a pure, I can write a small V I, and this is nothing but RT by P as far as the ideal gas is concerned. Okay, and that is same as V I G, right. So, for the pure case of the component I, molar volume is nothing but RT by P, and that is same as the partial molar volume of that component in ideal gas. Now, let us take this definition and extend this to obtain the delta V mix for the case of ideal gas mixture. So, this would be the change in the volume of the mixture in ideal gas. Okay. And this by definition is nothing but summation Ni Vi bar minus small Vi. Okay. Now, this of course, small Vi and this Vi bar is equal to 0. I mean small Vi bar is nothing but equal to Vi, and hence this is nothing but 0, and thus this is 0. Okay. So, that is one of the property of ideal gas mixture, that the volume does not change upon mixing. That is what it clearly says, that is why delta V makes ideal gas is equal to 0. Okay. Well, it is understandable also, because we also consider ideal gas does not have any volume, particles as such does not have any volume as such, right. Not that ideal gas does not have volume, ideal gas of course has volume, but ideal gas particles do not occupy any specific size itself, and hence they can pass through each other when they mix. Okay, so they do not collide as such. The particle does have any kinetic energy, but they do not collide with each other, they collide with the walls. So, considering that the molecular nature of the ideal gas, this is kind of intuitive, that the volume essentially should not change upon mixing, okay, because the particle does not have any specific size or does not occupy any specific volume as such particles. Okay, so that is the subtlety in this kind of definition. So, let me now extend this exercise to internal energy. Okay. Now, internal energy of an ideal gas depends on the temperature and number of course particles. We can also write this as summation Ni and molar internal energy, which only depends on temperature, because the internal energy contribution of an ideal gas is due to only the kinetic energy, which of course has a direct relation with the temperature. Now, if you look at this, then straightforward to obtain the partial molar internal energy, okay, which will be nothing but UIT, right, because this is nothing but del U by del Ni, right. So, this is clearly UIIg is equal to UIT, and now if you have been asked to find out delta U, that means change in the internal energy upon mixing, then the answer would be this is 0 and hence this has to be 0, right. So, that is also the case for the delta U. So, we have the volume change 0 for the ideal gas mixture, internal energy change 0 for the case of ideal gas mixture. Okay, so, we can also extend this thing for enthalpy. Similarly, we can show that the delta H Ig mixture is 0, okay, and how do we do that? We start with our definition that Hi is nothing but Ui plus Pvi, or we can say here directly partial derivative of H here is, okay, directly we are extending it as we have done this, we have shown this particular expression, that the thermodynamic relations as we write it for the pure component can be extended for this, and we can extend it for the partial molar properties as well. So, I am just writing that. Now, given this, I can write this as PVI G is nothing but RT and UI Ig, which is nothing but HI bar Ig, because this is UI small, okay, molar volume or smaller one. Okay, so, this is in other words, this is a molar internal energy. Okay. So, with this you have molar internal energy plus RT of a component I, okay, and this will give you HI Ig, that is your molar enthalpy of component I. Okay. So, this we have calculated, right, this we have derived it earlier, as we have shown there, that UIG is nothing but UI, right. So, I could actually write this also in order to have a clear thing. This is nothing but saying it this, right. So, this is equivalent. Okay. So, this I write it usually for the pure component I write it like that, but for the case of mixtures is better that we write it in this way. Okay, so with this definition, of course, that Hi bar is nothing but the molar one, then I have now that delta H mix ideal gas is nothing but summation Ni Hi bar minus, okay, I this, or I can write this as summation Ni Hi bar minus Hi. Okay, for the basically this is for the pure component, right. So, this is what we are trying to write, and since this is same as this, as we have seen here, okay, molar component of this has to be equal to 0. Okay. So, it is a straightforward exercise of systematic analysis here. Okay. I would like now to extend this to the entropy, but before we proceed further, we must understand a bit of the pressure component in the gas mixtures of ideal gas. Okay. So, for the case of the gas mixture, or any mixture basically, right, we can define something like partial pressure, okay, which is usually defined by a symbol Pi, and this is nothing but the total pressure multiplied by the mole fraction, okay, in the gas phase. I can write this as Ni number of moles of the component I divided by the total number of moles in the system, Ni by Nt. If it is an ideal gas, Pi is Ni by summation Ni, right, and here P can be written as summation Ni RT by V. So, this gets cancelled. So, this is nothing but Ni RT by V, which is nothing but the pressure of the system with Ni moles of component I at temperature T and V, right, and this Pi is nothing but Pi with all the components in this composition at temperature and volume, right. So, this Pi becomes P here for only ideal gas. So, let us try to understand this a bit. So, when you mix it, what happens to this pressure? So, let me consider the case that as I said, we are trying to reach towards understanding how to bring the entropy calculations or the change in the entropy upon mixing. So, what I am going to consider is a system where you do have a couple of components which are separated something like this, and they are separated by this partition. Okay. So, you have of course, molecules here, here and here. Okay. Upon the removal of the partition, you expect a mixing of these particles here, right. So, the effect of this removal of is basically effect of removing the partition and mixing the component if you think about that, a particle which is here was able to only access the volume available in this region. So, once you take out the partition, the same particle now have more volume to access, right. So, there is a greater volume within which the particles can move. So, that is one effect of removing the partition. Okay. Now, when you have greater possibilities, because the particles can move various different locations and all the particles can access more possible locations, leading to more such arrangements, or in other word, if you think from the concepts of the number of possible conformations, number of possible access, or leading to variety of different in the molecular level conformations. this would also indicate that there is an increase in the disorder because of the fact that the particles are moving and they are able to access more. So, essentially this indicates that there should be now increase in the entropy upon mixing the particles, even if it is an ideal gas. Okay, that is something which is very interesting. So, we notice that for ideal gas the change in the volume upon mixing is 0, change in the internal energy enthalpy should be 0, but when it comes to entropy, it appears that upon removing the partition, the possibilities of access to the different volumes increases for each particles, leading to more randomness in some sense, right. So, that is something which we would like to now explore. Okay. So, let us see what happens now. Why did we describe the pressure? Because of the fact here, initially each of them had like the pressure corresponds to their number of molecules, number of moles present in that, and then once that is mixed, each of them, each species in some sense. So, here for example, in this case I have mixed it with all same color, but we can consider that this is let us say different colors indicates different kind of species, and when you mix it you have all kind of arrangements here. Okay. Now, the question is very clear, is that of course, you have the pressures which is due to this pure one, and when they are mixed, each of them is contributing to the total pressures. So, each species has something called partial pressure, that is what we talked about here, right. This is the partial pressure corresponding to each species, right. So, let me try to graphically explain what happens, how do we interpret this whole behavior, because it is an ideal gas. So, for example, these black particles are not interacting with the green particle, and same for this red and green and red and black. The only thing which they are able to do is they are able to access more volume, okay, compared to the case where they are earlier, okay, because they are ideal gas. So, the equivalent representation considering particles do not interact, would be the following, where I can consider that, well, for a single species, let us say it's a black particles here which were at temperature T and P, the volume initially was let us say V I Ni T by P because of the ideal gas. Now, upon removing the partition, you have now much bigger space, all right. The same set of particle now can access more volume here, but this is now temperature T and V, that is the total volume now, okay. And essentially this volume now can be written as total number of moles R T by P, okay. And the final pressure, which is going to be Ni and P. P is the total pressure of the system, but the contribution due to this particular black particle would be Ni N by P, okay. So, in other word, what you are trying to say is that, well, the particle, this particular blue component is expanded, okay, our box is expanded such that the volume changes from V I to total volume V, and the pressure changes from its the pressure which was given P to corresponding P f, or in this case P I for example, okay, for the specific component, because each of them are independent. Okay. The only thing which is differing is the number of moles and the initial the volume here, okay, but finally the final volume is fixed. So, considering that, how do you now calculate the delta S from this exercise? or from this particular understanding. So, let us again look at it. Since T is constant here, okay, and I know that upon mixing, or even if expanding here, if T is constant, essentially what means that u T is constant, right, and now if u is T is constant, du is equal to 0, but du is nothing but T ds minus P dV, right. So, I can write delta S as 1 by T integral of P dV, okay, at constant T. Now, the relation I have to find out the delta S of this particular expansion of the volume of this particular component, and we can just look at only the pure component here at this point, okay, because each of them will contribute to the delta S or the change in the entropy, and since the entropy is extensive property, we can simply add it up. Okay, so delta S is here, right. Now, as I said, I am just going to look at the pure component. So, let us look at only the molar entropy change for pure component I, such that is from small v I it goes to v at t. Okay. So, you can consider here this is a v I, it goes to v here. Okay. So, with this I am saying delta S I at this point, let me just look at the entropy change, and then I am going to look at the molar entropy. Okay. So, let me just focus on the entropy part here first. So, delta S I is equal to 1 by T summation V I V P dV. Okay. The N R T by V, right. Of course, it is going to be an I. So, it is a pure component. Okay, so, R T comes outside, N also comes out here. So, this N is basically of that component V I V, and now we have dV by V. Okay. So, now I can look at now for molar entropy. Okay, which will be delta S I bar, okay, and I can just focus on R integral V I V dV by V. Okay. This is nothing but R ln V by V I, which I can write as R ln. Now, V here is a total volume. Now, total volume of the system in the mixture is related to total number of moles R T by P. Okay, so, that is something which you cannot ignore, because at the end of the day what I am trying to find out is delta S change from its original state, which was pure, to the final state. Okay. So, final state has other components also. Okay. So, when we connect this V here, total number of moles divided by Ni, okay, this essentially comes from the fact that V is nRT by P, N or NT total, okay, and Vi is Ni RT by P, right. For the same pressure, okay. So, the same pressure, this is the case. So, with this is going to be Y, 1 by Y rather. So, I have now an expression that delta S I is minus R ln S I bar here Y I. So, this is my change in the entropy of a component I upon in the mixture, okay, from the pure state to the mixtures. Now, given this, I have to now add it up for the other cases. So, if you add it up others will be straightforward, because delta S ideal gas mixture would be nothing but your summation Ni, okay, and delta Si, okay, because it is extensive. So, we are simply adding the contributions for each particular component, okay. That's a relation I am just simply adding here. So, delta Si ideal gas mixture is nothing but simply the summation of others. So, here I can expand it now, Sn I am replacing it this here, right, and now at this point right, if at this point if I divide this by, let us say if I consider Ni by n total n here or ln y here, then I can multiply n here, that is the total number of particles. Then I have a relation now, delta S ideal gas mixture as minus nr summation yi, this is a double r here which should not be the case. So, this will be now ln yi, okay. So, therefore, delta S I G mixture is minus nr summation yi ln yi, okay. So, this is how we have now come up to that expression which relates the change in the entropy of the ideal gas in the mixtures to the compositions of different components, okay. You can extend now this to obtain the delta G also, because you do have now all the information. So, let me just try to do that and that will be end of the lecture. So, the Gibbs free energy change would be delta G ideal gas mixture would be delta H minus T delta S, and since this mixture, and I am going to put here ideal gas, I am going to put here ideal gas, and we know from that this is going to be 0. So, with this delta G ideal gas mixture is nothing but plus nR T summation yi ln yi. So, you put it here, you get this expression, that is your delta G ideal gas mixture, okay. Similarly, you can also obtain the Helmholtz free energy change. So, basically the change in Helmholtz free energy. So, that is delta A I G mixture, this is going to be delta U minus T delta S, again this is ideal gas, hence I am putting it here, and this is for the mixture, okay. So, that is the beauty of thermodynamics, you know, the relations remain the same, only you are concerned now with the change of the individual properties here, okay. So, here of course, this is going to be 0 and this is still minus here. So, you plug in the same expression, you get again nRT summation yi ln yi. So, change in the Helmholtz free energy and the Gibbs free energy for the ideal gas mixtures is same. So, that summarizes the expressions which we wanted to calculate, or which we wanted to develop rather for the ideal gas mixture. So, let me summarize essentially all the what we have developed for the ideal gas mixture, just for the sake of having it here. So, for ideal gas mixture, we observed that the change in the internal energy is going to be 0, the change in the volume is also going to be 0, change in the delta H mixture is also 0, whereas delta S I mixture is minus nR summation yi ln yi. For the case of delta G I G mix, we are nRT summation yi ln yi, and Helmholtz free energy change is same as that of the Gibbs free energy, and hence we write the same expressions, okay. So, the only difference in between this delta S to other free energy is the presence of temperature, and the sign is positive. Okay, I think for now we will stop here, because we wanted to just look at first the ideal gas mixtures, and subsequently in the next class we are going to extend this understanding, and particularly for non-ideal gas mixtures. And the reason why we wanted to take this ideal gas, because this will always be used as a reference for our non-ideal gas systems or non-ideal systems. Okay. So, with this I will stop here, and I will see you in the next